Hello everyone and welcome to the NEx Webinar series. I am Aparna Deshmukh, Technical Director with NEx, and I will be your moderator for today's session. We are eager to learn all about our today's webinar titled Fire Performance of Concrete Structures Containing Fiber Reinforced Polymers. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may also use the question box to ask questions during the webinar, and our speaker will be happy to address them at the end of the presentation. So for continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion for 1 PDH. Your certificate will be available in ACI University under the certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the NEx Webinar series. So now let's get started with a short description of our today's webinar. The webinar will introduce the fire performance of reinforced concrete structures, covering research on reinforcing with fiber reinforced polymer sheets, plates, and glass FRP, GFRP in columns, beams, and slabs. The discussion includes the impact of insulation on fire endurance, recent guidelines in ACI Code 440.1122, and proposed advancements in designing GFRP reinforced concrete structures for fire resistance. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Dr. Mark Green. So Dr. Mark Green is an ACI Fellow and a Professor of Civil Engineering in Stephen J.R. Smith Faculty of Engineering and Applied Science at Queen's University. He studies the structural performance in fire of concrete structures, applications of fiber-reinforced polymers, FRPs in structures, sustainable materials and buildings, and best practices for working with indigenous communities. He recently served as a provost and vice principal at Queen's University. He is a member of ACI Committees 440 and 216, Fire Resistance and Fire Protection of Structures. So let's welcome him and I'll ask him to present.
Thank you very much for that kind introduction, Aparna, and I think we have the correct slides up there, so we can begin. And as mentioned, Mark Green, and I'm happy to be coming to you today from our traditional Haudenosaunee territory that we share with the Anishinaabe peoples here in Ontario, Canada. So with the outline, I'm going to start and talk a bit about fire safety in general, and particularly for reinforced concrete structures. And then I'm going to move on to fiber reinforced polymers and their behavior in fire, and particularly talk about FRP reinforced concrete slabs and then FRP strengthened beams and columns, all of these for applications in fire, and then look a little bit into design approaches, and finally some considerations for multiple hazards such as fire and earthquake for consideration. So fire safety is a major problem because building fires cause many deaths and also billions of dollars in damage every year. But the fire risk, it can be mitigated if we're careful with our design. And we do have to have fire safety because it is impossible to prevent all major building fires. So what we need to do is to make certain that even if there is a fire, that there is adequate safety. And there are several things that we consider in fire safety. First, fire prevention and avoiding fires where possible, but then suppressing it. That could be with sprinklers or firefighting, and eventually putting out the fire. Of course, we need, and a very high priority is put on the successful evacuation of people so that people aren't hurt or killed. But what I'm going to be focusing on more is about the structural integrity, because I happen to be a structural engineer, that during that fire. So it's important to consider all of these things together so that we have fire safety, considering important materials and methods. So the overall goal is life safety, particularly to limit the probability of death, injury, and that's the #1 goal. Property loss is also something that is a consideration, but the #1 emphasis is now on life safety objectives. And property protection is left more and more to building owners. So just to give a sense, remind people about some of the major disasters from fire. And a few years back in the UK with the Grenfell Tower disaster and the significant loss of life and the social impact of that disaster, but also over 20 years now, but the collapse of the World Trade Center from the combined impact of the airplanes hitting it and the ensuing fire that took that down. So it can have very significant consequences for fire. Now, most fires in buildings are not of the magnitude shown in those previous pictures. But what we need to do to make certain that we have life safety is we need to make certain that people can escape the fire. And certainly what we need is that we need for the building to stay in place and have structural integrity while that's happening. And also that parts of the building aren't going to fall and block people from escaping. And then also as part of the integrity of the structure, we also make compartmentalization is a big portion. So we want to try to keep the heat and the smoke into certain rooms where it started and not to come into corridors or into stairwells, etc., so that people will be might be overcome by smoke when they're trying to exit. And of course, we don't want the nearby buildings to be affected and spread to multiple buildings. And additionally, in certain cases that we need to think about extra provision for people who aren't able to escape, such as prisons, and difficulty moving, such as hospitals, and then also to make certain that firefighters are going to need to have enough time to put out the fire as well, because that's a big part is extinction of the fire is what we need to do. So I wanted to talk just a little bit about what some of the stages are of fire development, just so people have a little bit of an understanding about what happens. So when we have, there are three main stages, and really is defined by this flashover point that's really the transition, when it goes from having a localized fire to basically combustion of all exposed surfaces. So the when you're in the pre-flashover phase, generally the fire is in one rooms or a few things burning. And that's really, this is a real priority. It's in that pre-flashover stage that people need to certainly get out of the room that's burning and ideally leave the building altogether. Because once flashover occurs and everything is burning all at once, there's extremely intense heat, and it's certainly not possible to survive that if you're in that. However, from a structural perspective, the post-flashover stage is the most important, because this is most damaging to the structure itself. And finally, I'll emphasize that the flashover here, it occurs when sort of that hot layer of gases reaches about 600 degrees centigrade. So in Fahrenheit, that would be a little over 1,000 degrees, maybe about 1,100 degrees. Sorry, I didn't provide the conversion right on the slide. So I'm going to talk a little bit then about how fire is accounted for in structural design. And these show some pictures of a large building tower in Madrid, Spain, that had a massive fire, and portions of it collapsed as a result, just to once again remind you about some of the significant consequences that fire may have. So what we need to have is to have some fire resistance, and that is provided in many members of the structure. And there are two main things that we're worried about. One is we want to have this effect of compartmentalization so that the fire and smoke stay in a limited area. And then also we want to prevent structural collapse during the fire. So this is often called passive fire protection, as opposed to fire protection that's more active, such as putting sprinklers in a building, etc. And an advantage of the passive fire protection is that we know that it will be in place. So, you know, active fire protection is great, such as sprinklers, but if something goes wrong, if the water supply gets disrupted, etc., such as what happened in the World Trade Center, that then the sprinklers won't work. And you need to have this backup of the passive fire protection. So fire resistance is defined as the time to failure of a member when it's subjected to the standard fire. And generally we're talking about fire resistance for a member. Ideally, we would want to be looking at the whole structure, but generally we're aiming to look mainly at member by member categorization for fire resistance. So looking at slabs, and then looking at beams, and looking at columns, etc. But the overall aim is for the overall structure to behave well in that time. So when we're looking at that and trying to do some designs and understand fire resistance, most of these that they're either used for design calculations, or more often they're used in furnace tests to evaluate the fire resistance in the test. And in these curves, the first two, the ISO curve and the ASTM curve, and the blue and the green curves here that are coming up here, and they go up, once again, these are it goes up to a plateau of over 1,000 degrees centigrade. So that would be well over 2,000 degrees Fahrenheit. And once again, I have only provided these in Celsius. But you'll see that there are two other curves that I plotted on here. The red one that is going up here very, very steeply, and then has a plateau. That's a hydrocarbon fire, which is quite often used if you're doing designs, say, for a tunnel or something where you might expect the tanker to be burning. But this black curve that I've shown here, where the temperatures increase to a point and then they drop off, that's what we actually expect in a real fire. So that, and so sometimes when people are designing for fire, they look at curves that are similar to this that are for, you know, and they'll look at a range of curves like this with different ranges that they might have a hotter fire that then decays earlier, or something that lasts a little bit longer with a decay stage that's later. And that's to recognize that usually in a real fire, it only burns as long as the materials that you have present are there, and then it has to degrade. However, for most standard fire tests for determining fire resistance, we're using these lower two curves, either the ISO or the ASTM. And so that is fairly standardized, but I think it's important to recognize that that doesn't necessarily represent what's actually going to behave in a fire. But those time temperature curves have been used for over 100 years now, and we have a good experience for them. It's there are some uncertainties when we change some of the conditions under which they're used, but generally it's fairly reasonable. So the other point to consider, so I talked about sort of the input, like what are the temperatures that we're exposing to when we're either designing or when we're doing a fire test. But the second thing to think about is, well, then how do we know that it's failed? So typically there are three main failure criteria, and these are done typically in the ASTM standard. So the first one is the loss of the load-bearing capacity. So if you're testing a slab and you have load applied to it during the fire exposure, if it falls into the furnace, then the test is over and it's failed. So I think that's fairly obvious. The second one is that you have the loss of the fire separation characteristics. And that's really the same situation I talked about, the slab on the furnace and you're heating from below. If the top surface gets too hot, then that might spread the fire onto the next floor. So that's the next consideration. And so the third one, and in a way it's really related to the first two, and this is about an unacceptable temperature increases at certain locations. And so the second one here, the unexposed surface, that's an average increase of 140 degrees centigrade. And once again, that's going to be about a little under 300 degrees, a little under 300 degrees Fahrenheit in terms of the increase in that unexposed surface. And for reinforcing steel or structural steel in a reinforced concrete slab, for example, if the temperature in the reinforcing steel reaches about 600 degrees centigrade, which is about 1200 degrees Fahrenheit, or a little less than that, then at that temperature, reinforcing steel and also structural steel, both of them have about half their original strength that they had at room temperature. And so that's where typically when we have fire, that we know that the loads are going to be less than we expect in other loading circumstances. And so that we expect that if the member has about half of its original room temperature strength, it'll probably be okay in the loads that are in required in fire. So then, in addition to knowing when failure is, we have some things to think about in terms of what the fire resistance time is, and some considerations I mentioned before about occupants escaping, time to for firefighters to put out the fire, etc., and even thinking about burnout of a fire compartment if firefighters can't get into. Now, this is where it gets a little messy because although we use these hour ratings, and I sort of mentioned these ideas, they don't necessarily line up that will match what is going to happen in the fire. But we tend to use a 1 hour fire rating for typical residential construction. And if it's a hospital or something like that, and we need a lot of protection, it might go as high as 4 hours, and then sometimes in other situations you go maybe 2 hours or 3 hours, depending upon the member. Typically columns might have a higher fire rating than beams and slabs, for example. So some of the things, if we're actually doing structural design for fire and how we would do that, is that we remember that the procedure can be done similarly to that at room temperature, but we have to remember that we're going to be looking at lower applied loads to the structure. We should think about things like thermal expansion, how that may affect our structure, and that you might have a different failure mechanism from what you would have at room temperature. So there are many complications, but just wanted to give at least a few ideas here. And maybe going back, the other thing to point out is that the strength of the materials will be affected and reduced at high temperature. So that'll be something important, and I'll come back to that later in the talk. So how you might actually calculate the structural resistance in a fire is, well, you could estimate the temperatures in the various members in the fire, and you could do a heat transfer model, or you could base it upon tests in a furnace of similar members. And then what you have to do is evaluate the material properties at high temperatures. What's their strength at that high temperature? What's their stiffness? Is thermal expansion a problem? And then you can calculate the structural resistance of the member. And then finally to look at, well, do you have other factors to consider? What about thermal expansion? Are other members providing thrust or confinement to your member? So that was a pretty high level overview of some of the requirements for fire performance in general, and particularly for reinforced concrete structures. So now I want to talk more specifically about fire and fiber reinforced polymers. So the slide that I have here shows a great figure of different types of fiber reinforced materials that we can have. And typically what we widely used in the industry are 3 types of fibers: carbon fibers, glass fibers, and sometimes aramid fibers. So you can see the carbon is the black fiber typically, and essentially white for a glass roving, and then sort of a yellowish color for the aramid, or Kevlar is a popular brand name for the aramid. Now, the 2 of these that are more widespread than the others are the carbon and the glass. And I should also mention that more recently that basalt fibers are starting to be used more and more. But in the work we've done for strengthening materials, so you'll see over here that you can see this is a roll of a sheet of a carbon sheet that would be used for strengthening purposes. And you can see here some a unidirectional glass fiber bar, for example, shown here. And the glass fiber bar would be used more often for a GFRP reinforced concrete structure. And then sometimes you have carbon fiber tendons are more often used for pre-stressing. I'm not really going to talk about pre-stressing here, but just as examples. So the other thing to emphasize is that we do have that all of the fiber reinforced polymers, that we have those 2 components. One are the fibers, so that's your F, and they're generally really high strength fibers. And then the second is the polymer matrix, and that's really what binds everything together and makes the fibers work together as one component instead of just an individual bundle of fibers like a rope. So I'm going to talk first on this topic about some of the myths that you might hear about FRPs and using them in a fire situation. So the first is that people say, well, we can't use FRPs because then it makes it combustible construction similar to, say, timber construction, etc. And of course, I'll sort of say why that's not true. The second myth is that structures with FRP will fail as soon as the FRP reaches what's called the glass transition temperature. And I'll talk a little bit more about what I mean by the glass transition temperature in a few slides. But once again, that's also not true. And then the third one is sort of the opposite. So the first two are basically like, well, you can't use FRPs. And then the third one is kind of, well, oh, we hardly even have to worry about the FRPs. We can use it just as long as the original structure could carry whatever loads we expect. And once again, this third one is not a bad way to start, but it's not going to guarantee that everything is going to be safe. And I'll talk a little bit about that. So the first thing is that it's combustible construction. Well, really it's not. For FRP repair, particularly on reinforced concrete structures, where the reinforced concrete itself is not combustible, and you're generally only putting a small amount of FRP on it for repair. But what you do need to do is you need to provide some flame resistance so it doesn't burn immediately, but it doesn't change the main characteristic of the structure itself, and it certainly doesn't make it combustible construction. For internal reinforcement, it is inside the concrete by definition, and so the concrete cover will provide the protection and prevent the type of burning that we're seeing over here. So then the second myth relates to the glass transition temperature, or sometimes we'll just say the TG. So the glass transition temperature that we're talking about here, I want to emphasize that this is a property of the polymer. So it's generally talking about for the polymer matrix, not the fibers. And so that it represents when the glass transition temperature is specified, and generally it's something like about for FRP repair materials that are cured on site, it's something like 60 to 80 degrees Celsius, so maybe 120 to 160, maybe 200 degrees for Fahrenheit. And then when we're looking at FRP reinforcement, internal reinforcement, typically they have higher glass transition temperatures than that. You're generally in the range of, say, between 100 degrees Celsius and maybe 150. So somewhere between 200 and 300 degrees Fahrenheit. And once again, this TG property, it's an important, and it's important to understand the effect. The main fact is that it affects the polymer. So it doesn't so much affect the strength of the FRP, but it affects its integrity and its bond with the concrete. So that's how we have to understand it. So we also want to remember is that for performance in the fire, it's not just how one material that's a component behaves. It's about how the overall member, and obviously ultimately how the structure will behave in fire. So that's also to remember that fire resistance is a overall member property and not dependent on any one material. So let's just see how some of this comes out in practice. And these are some examples of some FRP reinforced concrete beams. These are with glass fibers. And these are results of tests that we had. And in these tests, the slabs themselves, they obtained about 3 hours of 3 hours of fire resistance, and we had to increase the load even after this 3 hours to get failure. And so that we had about 400 degrees centigrade at the bottom of the bars was actually measured in those tests, particularly at the middle. So this figure here, this is the slab on top after we had finished the test, and then the furnace below. So that, and that's compared to the glass transition temperature of only 120 degrees centigrade. So the temperatures were almost 3 times as high, or over 3 times as high as glass transition temperature. So, so we still had adequate strength of the bars at the center, but what it did affect was the bond. And you'll see at the end here, we did get some pullout at the end, and that was as a result of the high temperature. And that pullout was the fact that we started to lose the bond strength. But just a little bit of overlap, and this overlap here is only about 8 inches that we had protected from the fire at the end. With that little bit of anchorage to protect the bond strength meant that we were able to have a successful fire test. And so these are some results actually showing what the temperatures are. So these are the temperatures that are at the end of the slab where it is protected. And so you can see the temperatures remain below the glass transition temperature in this region. And so that was quite important to have those to be able to anchor the bars into relatively cool areas of the concrete. So the third myth that I hope to dispel is about that, well, it would be sufficient if we're doing an FRP repair to just make certain that the original structure, without the FRP in place, can carry the loads that we would expect. And as I said, the second point, this is a good design approach. I think it's something that I would do first to say, okay, can it carry those loads? If not, then, well, maybe I wouldn't try to repair that if it has to perform well in fire. But I also recognize that, well, that's not going to be sufficient to ensure that it behaves well in fire, and I have to look to see if I need to do anything else. And so, for example, these are some tests that we looked at with FRP strengthened columns, and we did a whole raft of tests with circular and square columns. We used glass and carbon fiber FRP wraps. We also provided most of those columns with insulation on the outside to provide some fire protection. And then they were tested under axial load, and we wanted to obtain fire endurance ratings, and most of the columns performed very, very well. Most of them achieved a fire resistance of about 4 hours, and you can see in this figure it shows the test load that we had, and then the red bars are generally the amount that what they actually failed at, the columns, when we tested them after the fire exposure. So one of the things here, you'll see that these at the bottom, talks about the insulation. So we had different thicknesses of insulation on these different columns. But you'll note that this one column here, we did test without any insulation. And so yes, no problem. It could carry the loads without the FRP for the test load. But what happened is this column failed after about 3 hours of fire exposure, which actually might be okay in certain circumstances, but certainly didn't get the fire resistance of over 4 hours that all the other columns had. So that's where applying some insulation can be beneficial, even if you're in that category that I mentioned, where the original structure can carry the loads in the fire. And this other schematic that we actually give some credit for ACI people at Concrete International for thinking about trying to describe some of the work that we've done. So what we look here that, so you build a structure and it has a certain strength, and this is a corresponding service load. Well, what happens is you retrofit it at some point that increases both its strength and the service load. Then at some time later, you have a fire event. And of course, now this is an expanded time scale because this is 4 hours and this is years perhaps. But then this red line here represents the time temperature curve. And what happens, this black line is what happens to the strength during the fire if you have insulation present. So you can see that it slowly degrades and then finally you get some failure at this point. Now, what happens if you don't provide any insulation is we have a very similar situation as this. You increase, we have a similar service load at this point, but you don't provide insulation. So what happens is we lose a lot of strength of the FRP very early on, and then you don't have as much reserve for the other members. So we do start to lose gradually for the remaining reinforced concrete structure, but then we have failure at a much earlier time than we would have had before. And that's exactly what we observed in some of those tests on the columns. So I also wanted to talk a little bit about some future directions and some research work we've been doing in the last couple of years. One is about the importance of rational design approaches for doing this work. I mentioned the importance of the bond of the FRP to concrete at high temperature, and that's particularly for GFRP reinforced concrete structures. And then a little bit about multiple hazards such as fire and corrosion, fire and earthquake. So as many of you know, ACI has a new code for GFRP reinforced concrete structures. And although in the code language, there's not specific requirements for fire resistance, there is some guidance in the commentary about ways that you could achieve fire resistance by doing appropriate detailing. So the first thing that I wanted to mention is that one of the things we've recommended, if you can embed the GFRP reinforcement by about 12 inches or 20 bar diameters into a support or something like that, that should be adequate to ensure that you can achieve a 2-hour fire resistance of a slab without doing anything else. But if you don't have enough room for that embedment, some options we've suggested is you could thicken the slab near the supports in either of these two ways, or you could provide some externally applied insulation. That could be a spray applied insulation, or could use gypsum boards, etc., to achieve that, to protect those end anchorages. So a little bit more on the bond of the FRP to concrete at high temperature. We initially looked, these are some tests that we've done more recently in our high temperature furnace, and now we're looking at sort of longer lengths of GFRP bars embedded into concrete, and we've wrapped these with heating tapes such that we can control the temperature in 3 different zones in this case. So what we found here is that we did some tests in different regions here, and we found that when we have steady state uniform temperatures here, that we are getting falling off at temperatures that are above the glass transition temperature, as we found for shorter lengths as well. But this does the comparison of when we have a longer length versus a shorter length. And it does show that as long as the bar temperatures can be kept sort of in this range of 100 to 200 degrees centigrade, so we're talking about maybe 200 to 400 degrees Fahrenheit in this case, that we are getting quite a bit of benefit of additional length. As temperatures get hotter over the length, then that benefit falls off, and there's not as much, providing extra length doesn't make much of a difference. And you can see what happens here. So when we have, in this case, so we're pulling on this end and we have it very hot, that's what's normally expected in a fire scenario like what we had in our fire test, and then it cools down over this region, but it's still at 120, that's over water boiling temperatures we have here, but you can see that even visually it's not affected so much here. And so we can still rely somewhat on that bond. And so if we move on to another multiple hazards now, we've also been looking at combining fire with earthquake. And so in these cases, what we looked at is we provided some fire exposure, and then after we did the fire exposure, then we performed some cyclic tests, and we found that okay, yes, the fire exposure does change the behavior in the earthquake, but it's not for at least the exposures that we had up to 90 minutes, so not as much fire exposure as you might think. That the seismic behavior was still fairly reasonable in those cases. So some of my colleagues in Turkey at Istanbul Technical University did that work with us. We've also been doing work looking at fire and corrosion, and this work is with colleagues in India, Professor Sharma at Indian Institute of Technology in Roorkee. And so we're looking at these fairly large columns that have been corroded over time. You can see the results, and then they're actually tested for their performance and fire. And we did see some effects of the corrosion, but not huge amounts of reduction in the fire resistance for that. So we're looking to understand it a little bit more in material tests that we've been doing at Queen's University, and really looking at pullout and try to understand the bond performance at high temperature when we have that. And so you're seeing when we have corrosion. So you can see how we're setting up these pullout specimens for testing, and then exposing those into corrosive environments and corroding them at certain levels, and then testing them at high temperature to see how that corrosion has affected the bond performance. So that brings me close to the end of my talk today, and just wanted to wrap up with a few points and conclusions. Is that, and the first that is that concrete structures with fire reinforcement, we can have adequate fire safety, but we have to understand what's going on with the materials and what happens at high temperature. Certainly the glass transition temperature, the polymer, is important, but it doesn't tell the whole story about what's going on with the material. And so we will get reductions in strength of all the materials in fire, but the one that's particularly important, and this is for FRP reinforced concrete structures in particular, is the bond of the FRP to the concrete. And that is critical to make certain that you can have some end anchorage zones that are in a cooler region where you can get a better bond and anchorage of the bar. So certainly we need more rational methods of fire design for this, and particularly understanding what's going on. And And it is important also to recognize that you may not be dealing just with fire. You may need to think about, well, has your structure corroded? What's the effect of the corrosion? Are we going to have another natural disaster such as earthquake, et cetera, and how will the structure perform? So just coming close to wrapping up here, and just like to acknowledge all of those who helped to prepare these sets of slides and the presentation as shown here. And with that, come to the end, and happy to answer any questions that people may have. So thank you very much.
Yeah, thank you, Dr. Green, and thank you so much for excellent presentation and for generously sharing your vast knowledge with us today. I think this topic is very critical when it comes to using FRP in construction, and it's fairly new, and also it's one of the challenge which people face, I think, when it comes to using FRP reinforcement. So let's move to a question answer session. I have a couple of questions here. So my first question is, so you did mention that the glass transition temperature, which is 120 degrees Celsius, so is it a typical value for FRP bars? And there is another part of the question. It says, is there a way to increase the glass transition temperature by maybe using different resins or some insulation?
Yes, so so I did mention the bars that we tested were that I had there specifically about 120 degrees centigrade, so probably about 230 or something Fahrenheit, and that's fairly common glass transition temperature that you would get for most commercial bars. Some of them may be a little bit higher, but somewhere between 110 and 150, 160. Yes, it is, and it is possible to use other resins that are that will give you a much higher glass transition temperature. But of course, it's always a balance about are those resins more expensive? How's it going to affect the manufacturing? So these are other considerations to think about with those other resins. But certainly that is something that would be very interesting to pursue further about increasing for that, because it would help to enhance the performance.
Great. So on the same lines, we have another question which says, are there specific fire resistant coatings or treatments available for GFRP bars?
I'm not for GFRP bars as reinforcement in concrete. I'm not aware of any coatings as such that have been developed, and I think one of the impediments, once again, is to know what the coating material, how that might affect other performance at room temperature, the bond at room temperature, and all of these things. So I think that's certainly something that could be investigated as to how a surface coat, a new surface could be developed, and maybe a core be regular resins that are used, and maybe more high temperature resistant on the outside. That's an interesting idea, but I'm not aware of any manufacturer or anybody who has actually developed it as such. Yeah.
Okay, great. Thank you. So our next question is, do you think a 1 hour or 2 hour fire rating is possible for construction with FRP bars? And there is another follow-up question with it, like what would be the requirement of cover, or what the concrete cover would be required to achieve the desired rating?
Yes, so the amount of concrete cover, so yes, 1 or 2 hour fire rating is very achievable, and the amount of cover, I think the amount of cover is less of a concern as long as you can achieve some of the cooler anchorage lengths such that we put up. I think that that slide that I showed with the lengths that are from the ACI commentary, it actually does provide some guidance, and that should give you a 2-hour fire endurance with the covers that are regularly recommended, the cover requirements that are regularly recommended for slabs according to ACI guidance. So that's how we develop that amount. So it, I can't remember what cover we used. It was probably 1.5 inches, I think, 40 millimeters for that.
Okay, yeah. So do you mean like the cover is directly, the factor which can increase the rating? Because I have another follow-up question which says that, does cover requirement for FRP reinforced concrete elements need to be different as compared to the steel reinforced concrete elements to resist fire events?
So certainly you will get better performance if there's more cover than what you have for steel and the fire resistance. But that was something that we specifically looked at in the ACI guidance, in that we looked at how to make certain we could get, say, a 2-hour rating with the same cover that was required for other considerations. So not for fire, just what was going to be required for a GFR reinforced concrete structure. And then we did that by making certain that we had sufficient anchorage. So that's a little bit about that we have to be careful that because it's the bond of the bar to the concrete that's the most critical point of failure, that if we only have a lot of cover, then you'd have to have a massive amount of cover to really protect the bar if there's not a place where it's anchored more effectively, where things are a little bit cooler. It's also where we've said, well, then you also shouldn't splice bars, say, near midspan, for example, for the same reason, without doing something to better protect them in those in that region. So those are some of the things in the design guidance. So it and perhaps sometimes you might be able to get away with a little bit more cover. You might get a little bit less length that you might need to have the cool embedment, but the cooler embedment is probably more important than the thickness of the cover, say, near midspan.
Okay, yeah.
I hope that makes some sense.
Yeah, thank you. So our next question is, it says that currently ACI code 440.11 permitted that the fire resistance ratings are not required, like is permitted only in the situations where fire ratings are not required. So in your view, what is needed to include fire rating structural part of ACI 440.11?
Yes, so what that sort of came down to, we're looking to see if we can remove that for the next version. We had originally drafted it hoping that restriction would not be the situation, and that's where I showed those design provisions. That was ideally to be, say, yes, if you follow these design provisions, the slide that I had, then you should be okay. However, when we came to the code compliance, they felt there hadn't been sufficient number of ASTM tests that met the full requirements and that had been certified. So they're unwilling to, to go and say, okay, it's in the code mandatory language. So what we did, that provision was put in place saying, you can't use it there, but then there is some guidance in the commentary if you can demonstrate otherwise through other tests, etc. So that's why we provided that. So I'm quite confident with what we have in those commentary guidance, but for some of the evaluators that felt, no, they might still want to have a, a full ASTM E119 for a specific assembly that would be used before doing that. So people are now working, I think they've already done some of those tests since, we put those guidelines into place. So people are working on that. So hopefully that restriction will be removed fairly soon.
Yeah, hope so. Yeah. Thank you. So our next question is, are there documented case studies or real-world examples demonstrating the performance of GFRP bars in the fire incidents?
No, we don't. I don't think we have practical situations where GFRP bars have been used in a structure and then it has been in a fire. I'm not aware of that. We do have quite a few where of the fire endurance laboratory tests, et cetera, but I am not aware of a FRP reinforced concrete structure that has been subjected to fire in practice. Maybe there is one, but I can't think of one.
Yes, so similarly, we have another question which says, have there been studies on the fire exposure of concrete members wrapped with FRP versus members that are not FRP strengthened? So I think it's asking more how effective it is.
Yes, well, so I guess the question, I think we had this, may have had this before, I guess, like we didn't, in none of our tests did we actually do like a separate test where there was no FRP involved. However, there have been many other similar members that have been tested. So like the columns, like there are a lot of reinforced concrete columns that have been tested in a very similar manner to the ones that we've tested. So so that's right. So there is a benchmark against, say, the types of tests that we did on the columns, and then look in the literature against similar columns that have been tested where there's no FRP. So one of the things that you will note that what we did in our tests is that we always calculated the service load, the load that would be required during the fire test based on having the FRP present. So it actually means that our columns were tested under higher loads than if the FRP had not been in place.
Okay.
So, so it is a slightly different test. If the FRP hadn't been there, we would have tested under lower loads.
Okay, got it. Yeah, thank you. Our next question is, it seems your experiment for the embedment was for simply supported slabs. What about monolithic or fixed slabs?
Yes, we did simply supported slabs, which for that fire endurance, I think is the most critical because you only have that, right, you don't have any thrust effects or other things that can help you. If you actually have where, say, it's multiple spans, et cetera, you actually get some benefits, particularly if it's, say, if you were to have 3 spans and you're looking at fire in the middle span, that having the bars continuous over those multiple spans gives you some advantage for gives some advantage for having perhaps cooler embedment. Plus, you get restraint forces that develop that actually enhance the strength of, say, the middle slab in that. And that same effect is shown for regular reinforced concrete slabs.
Yeah, great. Thank you so much. We have one last question. So, do round concrete columns perform better than square columns when strengthened with glass or carbon FRP wraps? Are the FRP wraps negatively impacted by the sharp corners that are found in square concrete columns?
Yeah, so I think that's a question that's a little bit more for the room temperature performance, but I can answer that and then comment on the fire performance too, because there are some differences. So generally, the most because the effect is for confinement, so the largest benefit you will achieve is when you have a circle, and so square columns are not going to be as effectively confined as circular columns. However, we have very good design procedures for how to strengthen rectangular or square columns, and provisions for detailing, such as smoothing some of the corners and the edges. So you have to do some of that beforehand. Because if you were to wrap, and if it were going around a sharp 90-degree corner, then yes, that would damage the fabric and not give you proper results. So you do have to make some modifications to the columns at that. Also, similarly, it does turn out that in fire scenario, probably that square columns don't work out quite as well, partly because probably less to do with the FRP, but more about some of the internal confining mechanisms of the way in which you can do stirrup configurations, providing you can much more effectively confine the core of a circular column than you can a square column. And so for that reason, I think that circular columns will quite often perform better in fire, like regardless of even having the FRP there, than would a square column. But we tested both square and circular for the FRP repair. We did find that the circular were better even in the fire performance, but certainly you could get adequate fire performance from the square ones.
Yeah, so we should have more round columns.
Yes, and maybe architects would like that.
Yeah. Thank you. Thank you again for answering all the questions. This ends our question and answer session. So I'll just go to a few more slides. So these are our upcoming webinars at ACI University. Please visit aciuniversity.com to register for our upcoming webinars. And again, thank you so much for your presentation, Dr. Mark, and also to the audience, thank you for attending. And I think we are pleased to have you all, and it's a good attendance we have been getting so long. So thank you so much for your support. Bye-bye.
Well, thanks for all your help, Aparna. Yes, bye.